Hey, I'm Dr. Weinstein. Today, how a deep-sea sponge's skeleton inspired engineers to build lighter, stronger skyscrapers and bridges. For a century and a half, engineers have been refining structural trusses. Bridges, cranes, towers, skyscraper frames, all of it stands on these lattices of beam. And now it turns out, a creature living on the ocean floor has a skeleton that bears loads better. And that skeleton is made of glass. Fragile, breakable glass, and it outperforms our steel trusses. This is a deep-sea sponge with a poetic name, the Venus flower basket. It looks like an elegant woven vase or a lacy goblet spun from the finest threads. Extraordinarily beautiful, it was even given as a wedding souvenir. But behind that beauty hides an engineering marvel we only just figured out, and it has been carrying this secret for millions of years. This sponge lives deep. Hundreds of meters, sometimes kilometers below the ocean surface. Down there, the pressure is crushing and cold currents pull constantly. The sponge is anchored to the seafloor and can neither hide nor swim away. It simply stands and holds for years, for decades. The water presses, the currents bend and twist, and it holds. And here's the remarkable thing. Its skeleton is made of neither bone, nor chitin, nor cartilage. It's made of glass. Literally, silicon dioxide, the same substance as window, glass, and sand. A fragile, breakable material that cracks at the slightest knock. And from this glass, the sponge has built a structure that stands under the pressure of the ocean. How? Here's the same riddle that keeps engineers up at night. Glass handles compression well, but behaves terribly under bending and impact. It shatters. You don't build bridges and towers from glass, it sounds absurd. Yet the sponge has built a delicate glass tower that stands on the seafloor under crushing pressure and shifting current. Which means the material isn't the point. And that's the key to the whole story. The sponge's secret isn't some wonder glass. Its glass is completely ordinary. The secret lies in how that glass is arranged. In the geometry of its skeleton, in how the beams are positioned, how they intersect, how they transfer load to one another, shape matters more than substance. And it's precisely this shape that scientists examined under the microscope. Before we dive into the sponge, let's sort out what a truss is. A truss is a structure made of beams connected into a rigid lattice. They're what hold bridges, cranes, towers, and building frames together. Think of a lacy railway bridge or the Eiffel Tower. Those are trusses. The idea is simple. Instead of a solid wall of metal, a network of beams. Economical, light, and strong. Why not just build from solid metal? Because that's impossibly heavy and expensive. A solid steel beam of the necessary size would weigh a ton, and you need something else to hold it up. A lattice removes all the excess metal, leaving only what's actually doing work. The strength stays. The weight drops dramatically. That's the very principle that makes skyscrapers possible. And here's the key metric in all of engineering: strength to weight ratio. Not just how much can it hold, but how much can it hold per kilogram of its own weight. Because a structure has to support not just the load, but itself. The heavier it is, the more strength goes to waste just holding its own mass. Lightness isn't a luxury, it's what makes the whole thing possible. This bites especially hard at heights and in flight. Every extra kilogram in a skyscraper presses down on everything below it, demanding thicker columns and a more powerful foundation. Every extra kilogram in an aircraft is fuel burned. In a rocket, it's mass that doesn't make it to orbit. That's why engineers fight over every gram. Any idea that helps is worth its weight in gold. How is an ordinary truss built? Usually it's a square grid of beams, verticals, and horizontals, like graph paper. But a plain square grid is a weak fighter. Under load, the square easily shears into a parallelogram and the structure collapses. So diagonals are added to the square's bracing members. A diagonal turns a square into two triangles. And a triangle is a rigid shape. The triangle is every engineer's favorite shape. You can shear a square without changing the length of its sides. But you can't shear a triangle. To fold it, you'd have to stretch or compress one of its sides, which means a triangle holds its shape by itself. That's exactly why every truss is full of diagonals. They split the squares into undeformable triangles. That's the ABC of construction. And for a century and a half, all structural engineering has rested on this principle: a square grid plus diagonals. Different truss configurations have been invented and refined since the 19th century for bridges, train stations, towers. The schemes were named after their inventors, put in textbooks, written into building codes. It seemed the subject was closed, everything worth discovering had been discovered. And then the sponge. Let's look closely at its skeleton. It's a cylindrical tube woven from thin glass beams, and those beams are arranged far from randomly. There are verticals and horizontals, the familiar square grid any engineer would recognize. But there's also something more, and that something is what makes all the difference. On top of the square grid, the sponge's skeleton carries diagonals. Not just one family of diagonals, but two crossing each other. One set spirals one way, the other goes the opposite direction. They intersect, creating a network of diamonds overlaid on the network of squares. Square grid plus double cross diagonals. A simple combination that engineers somehow never tried. You might think, so what? Our trusses have diagonals too. But we typically use one diagonal per square brace running one way. The sponge has them crossing in both directions, not in every cell, but alternating in a clean, regular pattern. This isn't a small detail. As it turned out, exactly this detail changes the behavior of the entire structure. To understand why two diagonals matter, let's first see what one actually does. When a force tries to shear the structure one way, the diagonal running across that shear resists it, it stretches or compresses, and keeps the square from collapsing. But if the force comes from the other direction, that same diagonal is almost useless. It only protects against shear in one direction. And the trouble is, loads are rarely polite. Wind comes from different directions, currents twist, a bridge shakes from passing trains. The structure gets pushed right, then left, twisted one way, and then the other. A single diagonal covers one direction, but the structure stays exposed from the other. You need an answer for every direction. And that's exactly what two crossing diagonals provide. One resists shear in one direction, the other covers the opposite. Together, they protect the structure from being twisted any way at all. No matter which direction the force comes from, one of the diagonals is always in position to resist it. The blind spot disappears. The structure has no weak side. Scientists put this to the test. The team of Fernandez, Eisenberg, Weaver, and Bertoldi built computer models and physical samples of both structures, then loaded them until they failed. The result was unambiguous. The sponge's geometry at the same material cost held significantly more. Not a little more, substantially more. The glass creature beat our steel schemes. The numbers made an impression. The sponge-inspired lattice proved to be roughly 20% more rigid and stable under twisting loads than the best conventional truss with the same amount of material. 20% at the same weight. In structural engineering, where engineers fight over fractions of a percent, that's a serious figure. From a creature with no engineering degree, and here it's worth pausing to feel what torsion twisting actually means. Imagine holding a long beam at both ends and rotating one end while the other stays fixed. A twisting force tries to turn the structure around its own axis, wind it like a wrench. This is one of the most demanding types of load, and many trusses handle it poorly. The sponge's double diagonals handle it well, but improved torsion resistance isn't the only advantage. The double diagonals do something else important. They spread the load more evenly across the entire lattice. In a standard truss, some beams carry the main stress, while others are nearly idle. In the sponge scheme, the diagonals route forces along more paths, so more elements share the work. Each beam does less, the whole structure does more. A good analogy, a road network in a city. If there's only one route through town and it gets blocked, everything seizes up. If there are many parallel routes, the traffic spreads out and the jam disappears. The double diagonals create more roads for forces to travel. The load finds more paths, spreads thinner, and no single element gets overloaded to the breaking point. This research was published in 2021 in the prestigious journal Nature Materials. The paper is titled Mechanically Robust Lattices Inspired by Deep-Sea Glass Sponges. Fernandez, Eisenberg, Weaver, and Bertoldi showed not just that it works, but exactly why. They connected geometry, mechanics, and load distribution into one clear picture, from a sea creature skeleton to an engineering blueprint. Now, where does this matter for us? First, skyscrapers. The taller a building, the more wind tries to bend and twist it. The building's frame has to resist this. If you use the sponge's scheme, you either get the same rigidity with less steel or greater rigidity with the same steel. Less steel means lower cost, lighter foundation, smaller environmental footprint. The sponge helps us build taller and smarter. Then, bridges. A long bridge is a textbook victim of torsion. Wind, asymmetric loads from traffic, thermal expansion, all of it tries to twist the span. The more efficiently a truss handles torsion, the lighter and more slender the bridge can be. A sponge geometry bridge could carry the same load with less metal. Lighter, cheaper, smaller carbon footprint, all from a sea creature skeleton. Next, aviation. Aircraft frames are built from metal and composite trusses. Weight there is the absolute enemy. Every gram saved is fuel saved over thousands of flight cycles. A more efficient truss scheme could make fuselage frames, wing boxes, or support structures lighter. Lighter means less fuel, cheaper operations, less exhaust, and over decades of an aircraft's life, the savings become enormous. And finally, space. Spacecraft and satellites are built from ultralight trusses. There, every gram is worth a fortune. Launching a kilogram to orbit costs tens of thousands of dollars. A sponge-inspired lattice could make deployable structures, solar panel masts, telescope frames, antenna supports lighter and stronger. The sponge from the ocean floor on a spacecraft in orbit, that's quite a journey. There's something beautiful in the fact that a sponge's geometry works equally well on the ocean floor and in orbit. Both environments demand the same thing: maximum strength for minimum material. The physics of structural mechanics doesn't change between the deep ocean and space. A good solution scales. That's exactly what makes this discovery so exciting. And as in all the best stories, there's no single hero here. Not the double diagonals alone, the square grid is still needed too, not the diagonals from one direction, they need a cross set. Not the material, only the geometry. The strength emerges from the system, from how the elements are combined and arranged relative to each other. The whole is more than the sum of its parts. Stop and appreciate the scale of this. The same geometry, square grid plus double cross diagonals, works in a glass skeleton the size of a palm, in a bridge spanning a river, in a skyscraper frame, in an aircraft wing, and in a spacecraft truss. From the ocean floor to orbit. Geometry doesn't depend on scale, it works everywhere. And here's the central conclusion of the whole story. A structure's strength is decided not only by its material, but by its geometry. The sponge built something from brittle glass that outperforms our steel schemes because its beams are arranged more cleverly. You can take the best steel and waste it badly. Or take ordinary glass and arrange it so it stands up to the ocean floor. Shape is also strength. Let's be honest, this doesn't mean all bridges will be redesigned after the sponge tomorrow. Construction is a conservative field, and rightly so. Mistakes cost lives. A new scheme has to be tested, written into codes, learned to be welded and assembled. Not every load even calls for this particular lattice. Nature supplied the principle and proved its strength. Implementation is years of work, and the challenges are real. Double diagonals mean more nodes and intersections, and every node has to be made, connected, and inspected. What a sponge can effortlessly grow on the ocean floor isn't always easy to weld on a construction site, and the gains depend on the type of load. Engineers are currently figuring out exactly where this lattice delivers maximum benefit and where it isn't needed. And that's completely fine. The sponge was solving its own problem, surviving the pressure of the deep, not building bridges for us. Our job is to spot the key principle in its skeleton and adapt it thoughtfully to our own needs. The idea of double diagonals turned out to be invaluable. How to weld them, assemble them, and write them into building codes, that's the engineer's work. That's always how good ideas play out. So, what did we really take from the sponge? Not its glass. We took the geometry, a square grid plus double cross diagonals that resist twisting from any direction and spread load across the entire structure. This idea is now being modeled, tested, and refined. The principle from the ocean floor has migrated into bridge and aircraft blueprints. A delicate sponge, a major clue. So, it turns out, an unassuming creature on the ocean floor proved to be a brilliant structural engineer. It solved a problem we're still wrestling with: how to get maximum strength for minimum material, and it solved it elegantly through geometry alone. And it's been doing this for millions of years, long before the first truss was ever built. Nature was ahead, once again at a kilometer's depth. And we've long admired the Venus flower basket for its beauty for that elegant glass weave, so like lacework. It turns out that beauty isn't decoration, it is the optimal structure. The pattern we find so striking is the direct result of the fight for strength. Here, beauty is a byproduct of good engineering, or perhaps the other way around. And that's almost always how it is in nature. And this story changes how we see the sponge. Before, a charming curiosity from the ocean floor, a souvenir, a museum exhibit, now a textbook on structural mechanics written by evolution. In that fragile glass, lacework hides the answer to a question generations of engineers wrestled with. Sometimes a scientific breakthrough is sitting in a museum case waiting for someone to look at it the right way. Put it all together. The Venus flower basket holds up the ocean on its glass skeleton because its lattice combines a square grid with double cross diagonals and therefore resists twisting from any direction and spreads the load across the whole structure. Scientists tested it and confirmed. With the same material, the sponge holds more. And now this geometry is being carried into bridges, towers, and aircraft. Think about how much excess weight costs us. Every ton of unnecessary steel in a bridge is a ton of mined ore, burned coal, emitted carbon dioxide. Every extra kilogram in an aircraft is fuel burned again and again, flight after flight, for decades. A smarter geometry isn't just a financial saving, it's less extraction, fewer emissions, a smaller footprint on the planet. Notice what the discovery actually is. The sponge didn't invent a new type of beam and didn't find a special glass. It simply added a second family of diagonals and everything changed. The elements themselves are the same, what changed is how they intersect and work together. The whole turned out to be more than the sum of its parts. Sometimes a breakthrough isn't a new component, it's a new connection between old ones. And one sobering thought. For a century and a half, thousands of brilliant people looked at trusses and didn't see the better option. Not because they weren't capable, but because they weren't looking. We'd settled into a familiar scheme and accepted it as the truth. Every field has these blind spots. And sometimes, to see past them, you just need to look at how nature solved the same problem. And nature has something no engineering bureau has: unlimited time for testing. Every organism that couldn't bear the load was a failed prototype. Every survivor was a working design. Millions of years of selection are millions of testing cycles we could never replicate on any test bench. Nature is the most experienced design bureau on the planet. And if one answer was found on the ocean floor, how many more are sitting right around us? Bird bones, hollow inside, and astonishingly light. Bamboo stalks that bend without breaking. Shells, honeycombs, spider webs, trees. Every living structure is a solution to the problem of maximum strength from minimum material. A whole library of ready-made blueprints. Almost nobody opens it. And this story carries a lesson in humility too. We're used to thinking of engineering as the pinnacle of human reason, and it genuinely is remarkable. But sometimes a simple sponge with no brain, no blueprints, and no calculations arrives at a better solution than we did. Not because it's smarter, but because it had more time and a stricter examiner. That's worth remembering. And the most valuable thing here is the approach itself. These scientists weren't sitting over equations looking for a new truss, they looked at a creature from the ocean floor and asked, how is it arranged? That single question is what produced the breakthrough. Sometimes, to solve a problem, you don't need to think harder, you need to look sideways to where the answer already exists. Here's the thought to leave with. For a century and a half, we were convinced we knew everything there was to know about structural trusses. And yet the better answer was quietly standing in the dark on the ocean floor the whole time, asking nothing of us but attention. How many more ready-made solutions are waiting in places we simply haven't thought to look? So next time you see the delicate glass lacework of a Venus flower basket in a museum, don't hurry past. That sponge knows something about strength that engineers only just figured out. And the bridge you drive across, or the aircraft wing that carries you through the sky, may one day be built to its blueprint. Nature figured all this out long ago. Our job is simply to look and ask, why does that work? Thanks for watching. You're definitely a little smarter now, and you know one more story about how humans borrow their best ideas from nature.